To finish up the section on rotational dynamics, we are going to be doing a lot of demonstrations in the classroom. So for the purpose of our notes, I want to make sure that you concentrate on getting down the definitions and the formulas. And then we will actually be applying them to some hands-on experiments for you so that you can kind of understand a little bit better. So for Newton's second law, hopefully from last semester, you remember that the law stated force is equal to mass times acceleration. And technically, it was the net force. So remember, if you had more than one, you wanted to combine those together. So for rotational motion, we are going to replace force with torque. And remember, when you see it written out, it's that curvy little t. And we will replace mass with moment of inertia, which is our I. And remember, moment of inertia is something that depends on the amount and the distribution of mass. So how far out are you from the axis of rotation is going to be really important. And then lastly, our acceleration will be replaced with angular or spinning acceleration. So when we put these together, instead of F equals ma, we will have torque equals I alpha. And then I wrote down what each of those variables mean for you over to the side right here. And remember, Newton's second law was the net force equals mass times acceleration. So when we look at the rotational version, it's actually the net torque as well. So again, if you have more than one torque, we need to combine those together, and it will be that total that's going to equal moment of inertia times the rotational acceleration. For this question about the disc and the hoop, this is a demonstration that we will do in class, so make sure you bring your notes with you, because when we discuss the results, I would like for you to write down which of those two things wins. Next, we're going to look at angular momentum. So just like we had displacement velocity and acceleration, and then an angular version of those, we will be doing the same thing with momentum as well. The variable that you see for angular momentum will be a capital L. And angular momentum will get conserved just like linear momentum. So let's come up with our formula. To refresh your memory, I have linear momentum. Remember, it was a lowercase p, and it was equal to mass times velocity. So what we're going to do is replace the linear momentum with the angular or rotational. We also call that the spinning momentum. That gets replaced with a capital L. In our rotational world, mass will become moment of inertia, because it's not just the amount of mass, it's how distributed that mass is. And then lastly, our velocity becomes angular velocity. The units for angular momentum will be kilograms times meters squared. That comes from the moment of inertia. And then we don't have to write the radians, but we do still need to show that we're dividing by the seconds from our angular velocity. So again, I went ahead and wrote out what each of those variables stand for. Whenever you see spinning, that can also be angular or rotational. And lastly on this slide, the right-hand rule tells us the direction of angular momentum. Now this is something new, and I have to show you in person to demonstrate how to use the right-hand rule and what it means. But for right now, I want you to understand that the right-hand rule is going to tell us the direction of angular momentum. In your notes for the bicycle wheel example, this is something that we're going to do in class together, so just leave some space and we'll revisit this when I see you in person. Again, another example you can look forward to. We are going to ask for volunteers to sit on a rotating stool, and I will put weights in your hands and spin you around, and then I'm going to ask you to pull your arms inward. And we will discuss what happens and why according to the conservation of angular momentum. Mathematically, we are going to look at an example for the conservation of angular momentum, so I'm going to walk you through those steps. We have an example of an ice skater. She is going to begin a spin. It says his arms out, but the picture's of her. Sorry, I didn't match that up very well. But our ice skater has an angular velocity of 2 radians per second and a moment of inertia of 6 kilograms meters squared. As the spin proceeds, the skater will pull in his or her arms and decrease that moment of inertia. It was 6, now it's 4.5, and we want to know the new angular velocity, so how fast will they be spinning? So to set this up, we want to show that angular momentum will be conserved. Just like when we talked about regular momentum, that means our before and after are going to be equal to each other. So in this case, instead of a collision occurring, the before will be arms out and the after will be arms in. So mathematically, we are going to say the initial angular momentum will equal the final angular momentum. So when we make that substitution, instead of initial angular momentum, we're going to say initial moment of inertia times initial angular velocity. And then for the final side, we're going to do the same thing and substitute. Moment of inertia times angular velocity. At this point, we can plug our numbers in. So remember, we started out with a moment of inertia of 6 and an angular spinning velocity of 2, and then decreased our moment of inertia to 4.5, and now we're solving for the final angular velocity. You should come up with an answer of about 2.67, and that would be radians per second. So if we look at the original angular velocity compared to the final angular velocity, notice how it got bigger. I kind of give you a little bit of a description here. Okay, the moment of inertia for the final version and the angular velocity of the final side are going to exchange with each other. So before the arms were pulled in, when the arms were still out, we had a large I and a small omega. And then after the arms are pulled in, it switches. Now we're going to have a smaller I and a larger omega. They will trade with each other to balance out in order to keep those totals the same. So I wrote you a little bit of a description. This actually kind of spoils one of the demonstrations. It tells you what should be happening, but again, we're going to do this in class so that you can experience for yourself. When the arms are pulled in, this makes the moment of inertia smaller, and in order to keep that angular momentum the same and have it be conserved, that angular or spinning velocity must increase. So you should see that when we're on the rotating stool and you pull your arms in, that person should spin faster. For the diver example, we start out with a diver that is stretched out versus one that's spinning. So think about how the angular momentum would be conserved. So a reminder that angular momentum is moment of inertia times angular velocity. If one of those two variables is big, the other one has to be small, and then vice versa, it trades right here. So that means as soon as a diver jumps, they go into that tuck position, and what that does is decrease the moment of inertia so that they can spin faster and get more flips in. And then think about what happens just before they enter the water. What does a diver do? How do they change that distribution of their mass? And why would they do that? So think about those questions and see if you can answer that on your own, and then we'll talk about it again in class. And I have one last slide for you. I don't know if this cut off in your notes or not, but you do need this vocabulary term. This word is precession. And again, we're going to use the bicycle wheel in class to actually demonstrate what's going on. But I want you to write down for right now that when you torque a top, so if you apply a twisting force, then the top will precess. So think about what it means when you apply a twisting force to something, how it's going to make that object start rotating. And then in class, we'll look at an actual top and the bicycle wheel and see what precession actually looks like. That's it for this chapter. And again, I hope you show up to class for the next few meetings because we are going to do a lot of fun demonstrations together. I'll see you then.